In this video, we're going to continue our coverage of ANOVA by working a very specific example. And in this example, we're going to examine if there is a statistical difference between different sectors of the economy for the number of new locations opened in 2023. Now, these are fictional data, but these data represent the opening of businesses across these different sectors. And so what we have here is we've identified 5 different groups. And so our first group include hardware stores, our second group are cannabis retailers, our third group are convenience stores, grocery outlets, and restaurants round out our 5 groups. Now within each group there are going to be 7 businesses that that have been randomly selected across Ontario in terms of those individual businesses opening up new locations. And we need an outcome measure here. And so the outcome measure, as already alluded to, are the number of new locations in Ontario in 2023. And so what we really want to focus on here is, does the sector have an advantage, if you will, or demonstrate a pattern in 2023 of opening up new locations. And in doing so, we take the null hypothesis statistical testing approach, where we first state the null hypothesis, in which the average of the 5 groups, so there are 7 businesses in each of the 5 groups. When we calculate the average of each group, though, the null hypothesis will state that they will not be different from each other. Now, with ANOVA, when we're dealing with more than 2 groups, the alternative hypothesis is a little bit more involved. And so one alternative hypothesis, this would be an H1, so this is the typo, this would be H1, and so would this, but we would find that mu1, which would represent the population represented by the first group, is not equal to the second group, but is equal to group 3, which is equal to group 4, which is equal to group 5. And what you see here are a number of different alternative hypotheses that are possible. So when we take a look at ANOVA and we have more than 2 groups, we only have one null hypothesis, and it's always stated the same way. But as long as the alternative is not the same as the null, it's an alternative. So the equal signs, you can only you might only have one not equal to sign. You might have 2, but even if you have 1, they would be in different locations. So this gives rise to a very large number of different possibilities. Now, this gets to be a little bit cumbersome, so we ask the question, is there anything simpler? And there is. And so with ANOVA, we would typically just state the alternative. Here I have it correctly with H1, that the alternative hypothesis is that HO, the null hypothesis, is false. Not all the mu's are equal, and by stating it this way, we capture any of these possibilities when we have more than 2 groups. Now, what's next here, once we state our hypotheses, now that we know our research design, is we conduct the study, we collect all the data, and is this a true experimental design? No, because we're not randomly assigning businesses to the different groups. We predetermined what each group would be, and then we would randomly select businesses that open up new locations to be part of those groups. So once we collect the data, and we'll see some fictional data here on slide number 9, the next step is to make that table of the raw data. And then we make a decision on the statistical analysis. And this particular statistical analysis will be a one factor. There's only one factor in this study, and that's the type of business. And we had 5 levels of that. Now, this does not involve repeated measures, because once we take a measure from one business, we don't take another measure from the same business. We don't repeat the measure. So this ends up being just a simple comparison between the different groups. And what we see here is a table summarizing the raw data collected from each of the individual businesses that qualify under each of the 5 groups. So what we see here in group 1, which represent hardware stores, this is one particular hardware store that opened up 4 new locations in 2023. Likewise, in group 2, the first entry is one business of a cannabis retailer that opened up 5 new locations, and so on and so forth. And so the first step whenever we have these data is that we calculate descriptive statistics, which are the means and the standard deviation. And so here we can just take a visual and we observe that the second group had the highest average, followed by the fourth group, which were grocery outlets. And we have the standard deviations associated with each. Note that what I have here on the far right hand corner is something called the grand mean. And this is the overall average collapsed across all 5 groups. Now, in and of itself, the 5.77 is an average of the averages, is not particularly meaningful, but it is necessary when we calculate the analysis of variance. So the overall question we're asking here is, are the groups statistically different from each other, and if so, which group is different? And so essentially here we want to ask, how do the average scores, those are the scores we saw at the bottom of the table on slide number 9, vary with respect to each other, and how do those vary with the grand mean? And that requires us to measure variability among the averages, and so that requires us to calculate an average deviation score that we are going to square. So to summarize the ANOVA steps, and we'll step through this in these series of videos, is the first step is to calculate the sum of squares. And as the term suggests, we calculate squared deviations, and once we calculate those squared deviations, we then add them all up. The next step the next calculation is the degrees of freedom, and like we calculated a degrees of freedom when we originally calculated the standard deviation and when we calculated or when we performed the t-test, here we actually have 3 different degrees of freedoms that we have to calculate that we'll step through. In step 3, we then calculate an average deviation score that we'll refer to as a mean square. So the mean square is the specific terminology in ANOVA, but another word for that is variance. So if you go back to the first video and our coverage of descriptive statistics, you'll see that calculation of the mean square will fundamentally be the same as calculating a variance. And in this statistical procedure, where there are 2 mean square values to calculate, and then that will give us what's called our F statistic. This is what we call our obtained F statistic. This one here in step 4 is based on the actual data. So we perform a number of these calculations, and the F obtained is the test statistic that we will use to compare to a critical F value that we get from the F table. So the F obtained, once again, is based upon the data. The critical F value is based upon our type 1 error rate and our study design. So we can compute, or we can look up the critical F value without doing any calculations on the raw data yet. So in beginning with the first step, we calculate three sum of squared values. And the first one here is what's called the sum of square within. And this, as the term suggests, this is a measure of the variability captured inside the groups. And so this equation is calculated by taking the sum of the squared deviations, and so this difference here, this is a deviation score. Once the difference is calculated, then it is multiplied by itself. Now the x here would represent the first hardware store. So that is the first entry in the far left-hand column on slide number 9. So that first value on slide number 9 was a 4. We subtract 5.29, and that's the hardware store average. Once this difference is calculated, then you would square it. Then you would move to the next number, which is a 5 on slide number 9, which is the second hardware store business, and that number was a 5. Subtract 5.29, and you would square it, and then you would continue this for all of the data in the table. The shortest calculation here is the sum of squares between. So the sum of squares between, as the term suggests, has us computing a measure of variability between the groups. And so what we see here is the deviation score is we take the average of the first group, which on slide number 9 is 5.29, and we subtract the grand mean, which is 5.77, and then we would square it. Then we would repeat the deviation calculation for group 2, which is 7.86, subtract 5.77, square that value, and add it to the previous one we had calculated. So we would have 5 different deviation scores that each one is squared, and after the square it's added to each other. Now the sum of squares between requires a correction factor, and that's where the entire sum is multiplied by n, which is the number of cases per group, and in our example the number of cases is 7. And then finally the total sum of squares can be calculated a couple of different ways. It's just simply the sum of the sum of squares within and the sum of squares between, or can be calculated as the sum of the square deviations of each individual score and the grand mean. So going back to slide number 9, the first entry would be a 4, subtract 5.77, which is the grand mean. That difference is squared. Then you move to the next value, which is a 5 in group 1, subtract 5.77, square it, add those two numbers together, and you continue to add numbers as you move through the table on slide number 9 and calculate all of those squared deviations. So on the next slide here, these are all the ANOVA equations that you would use if you were to calculate, if you were to perform this manually. And so what we have here on the far left-hand side are the equations that we saw on slide number 11. And then ultimately what we need to move towards is calculating something called a mean square. And the mean square is another term for the variance. And so we have the mean square between, which is the sum of squares between, which was calculated using this equation, divided by the degrees of freedom between, which we'll see those equations here shortly. Likewise, the mean square within is matched by dividing the sum of squares within, that was calculated over here, and the degrees of freedom within. Now the degrees of freedom, there are three degrees of freedom terms that you would have to calculate. And this is what you would indicate with an ANOVA analysis. The degrees of freedom between, this is between the groups, that's equal to k subtract 1, where k is the number of groups. And in our example, we had 5 groups. So this would just simply be 5 minus 1. And in the next video, we'll actually go through and perform those calculations. The degrees of freedom within is n minus k, where this is capital letter N, which indicates the overall sample size, not the number between groups. We used lowercase n for that, but the uppercase N is the total number of businesses in our sample. Subtract the number of groups, and the degrees of freedom total is the total number of units, of cases, subtract 1. And we do this to work towards calculating the F obtained, which is our very important test statistic. So the degrees of freedom are used to calculate the two variances, the variance between and the variance within the groups, and we look at the ratio between those two. Now the mean square within, sometimes it's referred to as a mean square error. So that's something to be something important to note. And this indicates the variability that occurs by chance alone. The mean square between is the variability, the systematic variability that exists between the groups if there is a meaningful difference, or a statistical difference rather, between those groups. And so where the between is an assessment of true differences between the groups, we have to consider natural variability in the data, and that's what the denominator gives us. It's a variance not accounted for by any of the group differences. So what we want to eventually do is compare this number that we calculate through these equations to the F critical value. And to do that, we need the F table. So this is just an excerpt of the F table. And to do this, we always, unless stated otherwise, we always settle on a type 1 error rate of 0.05. And what we need is our degrees of freedom within and our degrees of freedom between. So our degrees of freedom between is a 4, and our degrees of freedom within is a 30 by using the previous equations, and we'll actually calculate that here in the next video on the next slide. And so by following the headings here we see degrees of freedom B for between for the numerator, and that would be a 4, which is 5 groups minus 1. We then locate our degrees of freedom, this is lowercase e for error, or within, and we determine that value to be 30, which is n, which is the total sample size of 35 minus the 5 groups. And we find the intersection point of 2.69. That's our critical F value. At the 95% or 0.05 error rate, those terms have been used interchangeably. For a degree of freedom of 4 and 30, that value is 2.69. And that's going to be the value we're going to carry forward here in the next video to perform our calculations. And so this ends this part of our ANOVA lecture.